Okay, so thank you everybody for coming. It's a pleasure to have with us JR, which is Jonathan Robbins, not Jonathan Robinson as I mistakenly called him in one of the announcements. And he'll tell us about work he did with a bunch of Russian about collective coordinates, asymptotics and domain wall dynamics in ferromagnetics.
So thank you very much. For being here. I'll say the names of these Russian collaborators. Arseni Goussev is our former colleague. Valeriy is here. And Sergiy Vasylkevych was a postdoc with us in Bristol. So I'll be speaking about two problems, some dynamical problems in ferromagnets, and more specifically, the motion of domain walls and one-dimensional ferromagnetic nanowires. But I'm going to frame the presentation in terms of this widely used approximation scheme, which goes by different names. One is collective coordinates. It's really a restricted variational principle. And it's used a great deal in these kinds of problems, but in lots of other fields too. And the power of this method is it's very efficient, and it gives you an approximation with not a lot of work. And the difficulty is that you don't know if it's a good approximation or not. It's uncontrolled. So in one of the examples, I'll talk about the simplified equations can be justified from some asymptotic calculations, and in the second one, they really can't. It's just really not a good approach. So the dynamical problems I'll be speaking of, I'll assume there's some underlying Hamiltonian structure. Now, there will also be dissipation. And the idea is that dissipation is added to the Hamiltonian system in some phenomenological way. So let me just start with a very simple setting, finite dimensional Hamiltonian mechanics, which let's say we formulated in terms of a variational principle in phase space. So H is the Hamiltonian expressed in terms of canonical coordinates, and P dot Q minus H is the phase space Lagrangian. And suppose instead of trying to solve the full problem, we're going to constrain Q and P not to be free to vary, but to lie in some constrained surface or submanifold that's parameterized by these parameters big X. And there are fewer of them, fewer X's than there are dimensions of phase space. And then substituting these parameterized expressions into the variational principle, we get some equations of motion for X. I'm going to take a different point of view, not the variational point of view. One reason being that in the examples we'll be discussing, there aren't natural canonical coordinates to use. And at least for the purposes of a formal presentation, and this really will be formal, there's some advantages to taking a coordinate-free and geometric point of view. So an alternative formulation, Hamiltonian mechanics, Hamiltonian dynamics. The ingredients are you have a manifold P, that's your phase space. It's finite dimensional, it should be even dimensional, and it's endowed with this symplectic form that's a closed non-degenerate 2 form. And in addition, you have the Hamiltonian function, and I'm going to call the Hamiltonian E rather than H, because H is going to be a magnetic field later on. And from these, then you get a dynamical system on phase space via the following prescription. You say that the Hamiltonian vector field, which describes the dynamics, is obtained from this equation here. You contract the unknown x with omega to get the gradient of the Hamiltonian. And since this symplectic form is non-degenerate, this linear system can be solved to get the vector field in terms of the gradient of h. And if you have canonical coordinates, then this is just Hamilton's equations as where you expressed in terms of canonical coordinates. And I'll refer to this equation, it'll appear various times as Hamilton's equation. It's just a way of writing Hamilton's equations. So what does constrained dynamics look like in this picture? So in our phase space, we still have our Hamiltonian E, and we introduce this constrained surface C. And given the Hamiltonian, we ask the following questions. Can we define from this Hamiltonian constrained Hamiltonian dynamics that stays on C? And if we can, how is this constrained dynamics related to the original dynamics? So here's the prescription. We can restrict the symplectic form, little omega, to this constrained surface C. That's to get this to form big omega. And we can restrict the energy function, the Hamiltonian function, just to the constrained surface. So we can write down the analog of Hamilton's equations in this form, but now we have this difficulty that while this restricted symplectic form is still closed, but it might be degenerate. And if it's degenerate, you can't necessarily solve this linear system. If you can solve it, then the solution is not unique. And so this is a problem in constrained dynamics, and there are various approaches, one being the theory of Dirac constraints. But in more favorable circumstances, this restricted symplectic form will be non-degenerate, so you can find this vector field Y, which will now define dynamics on this constrained surface. If this constrained surface happens to be invariant under the original dynamics, then the vector field Y and X coincide. So this would be the case if the constraint is, let's say, a consequence of symmetry, conserved quantities. If it's not invariant, then the restricted vector field and the actual vector field could be very different. But, and these are the cases where the approach is useful, if this constrained surface is nearly invariant in some sense, then the restricted vector field might be close to the actual one. So here's an example, not the one I'll be concentrating on, coming from quantum mechanics. So first, an abstract formulation, phase space is Hilbert space. And for a symplectic form, we just take the imaginary part of the Hermitian inner product. And for the Hamiltonian function on phase space, we just take half the expectation value of the Hamiltonian operator, which is some self-adjoint operator. And then this abstract version of Hamilton's equations is just the time-dependent Schrodinger equation. But now let me consider a specific example. So Hilbert will consider quantum mechanics for a particle on the line, so Hilbert spaces. L2 of R, and the Hamiltonian will take to describe a particle moving in some potential U of X. But now instead of allowing the wave function to be free, we'll constrain it to be of this form. It's the form of a Gaussian wave packet, and it's parameterized by this Q and P, and well, the modulus squared of the wave function gives the probability distribution, which will also be Gaussian, and it will be centered at Q. And the Fourier transform of this wave function, which gives the distribution of momentum, or its modulus squared does, will be centered at P. So this corresponds to some ensemble, which you can think of as being localized, and the measurements of Q and P are localized around the indicated values. It also has a width A, which could also be a parameter, but we'll leave it fixed for now. So we're just considering a constrained surface in our Hilbert space, which is two-dimensional, just parameterized by Q and P. And if we apply the prescription I described, we get equations of motion for little q and little p, which are just the classical Hamilton's equations, where this classical Hamiltonian little h looks like what you take to be the associated classical Hamiltonian plus corrections, which are the order of the width of the wave packet squared. So this is a very quick way of getting this result that's sometimes called Ehrenfest's theorem, which says that in some cases, in some settings, there's some sense in which quantum mechanics follows classical mechanics, but of course there are many qualifications that have to be added to that statement depending on the initial condition and the Hamiltonian, and also how the error terms will grow with time. In some cases, this wave packet evolution is a good approximation. In others, it's really not. And the variational principle doesn't tell you on its own. All right, so the problem that I want to consider is micromagnetics, and I know there are experts in the audience, but this will be some brief overview. So let me consider static problems first. So the quantity of interest is the magnetization distribution in some ferromagnetic sample. This is the density of dipole moments. And you're well below the Curie temperature. This density, it's a vector valued function. Its norm is fixed, and it's then characterized by direction, which will be little m of r. And the energy, the micromagnetic energy, is given by this expression here, where there are a number of terms. So the first term is in the gradient of this direction squared. That's coming from this exchange energy. It's quantum mechanical in origin. There can be some contribution depending on M. This is some material anisotropy. If there's an external magnetic field, HA, then there's a Zeeman energy. And finally, there's the energy arising from the interaction of the dipoles amongst themselves. And this U is the scalar potential of a field whose sources are the divergence of M. So this is one way to express the dipolar interactions. And U is a non-local function of the magnetization, and that's one of the things that makes the analysis of ferromagnets, of micromagnetism, very challenging. So the Euler-Lagrange equation for this energy is, well, this HF, H effective is just the variational derivative of the energy with respect to the magnetization M. The Euler-Lagrange equation is not that H variation has to vanish, it just has to vanish in the directions that are orthogonal to M, and this is coming from the constraint that the length of the lemma has to remain 1. We'll be looking at taking the domains to be thin wires, and then this description can be substantially simplified. So the wire to have in mind is the longest dimension is its length, width is next, the height is next, and then the width, which is meant to be coming out of the screen, is the thinnest dimension. The energy in this case, or you can replace it with a simplified energy, and this can be studied and analyzed in a rigorous way. Valeriy has done a lot of work on this. So anyway, here's the simplified energy. It's now local in M. And here's the exchange energy, and we just take the magnetization and just depend on the vary along the wire. We take it to be uniform in the cross section, and then there are these anisotropy terms which favor M to lie along the wire, so the one direction is along the wire, and penalize variations in the thinnest direction coming out of the screen. So M pointing in that direction would introduce dipole moments, which would have high energy. That's the intuition. Then the Euler-Lagrange equation can be written as, well, has the form of a Schrödinger equation for vector function M, where the Schrödinger operator is this matrix-valued operator with constant terms involving these anisotropies K1 and K2. And solutions depend on boundary conditions. So first of all, you have the uniform solutions where M is just constant along the wire, one way or the other. And you also have domain wall solutions where M going to minus infinity points in the opposite direction to M at plus infinity, and then you get this interface or domain wall separating the two asymptotically constant directions, and has this characteristic such tangent profile. So dynamics is given by the Landau-Lifshitz equation written here. So for non-equilibrium solutions, the dynamics of them is two contributions. The first is the Hamiltonian contribution, which describes precession of the magnetization around this effective magnetic field. And then there's a dissipative term, which is basically gradient flow with respect to the energy, but respecting the constraint that magnetization has to remain, length of M has to remain constant. And now the effective field takes this simplified form. There's an addition that will allow there to be an applied magnetic field H1 along the wire. There might be transverse components to the applied field, and magnetization can also couple to electric currents, and that's an important effect, and these can be included in this setting. So if you start out with an initial condition that's some perturbation of the uniform solution, that you will see, this will describe the dynamics. These are spin waves, which will be, this term is present, they'll be damped out. And in addition, well, now let's consider some domain wall solution, and we apply some applied field H along the wire. So this will cause, well, the simplest dynamics is that this domain wall will move with magnetizations oriented as indicated and field pointing to the left, then the profile appears to shift to the right because the domain that's aligned with the magnetic field will grow and the one that's aligned against it will shrink. And in addition, the profile might precess around the direction of the magnetic field. And these domain wall motions in one-dimensional wires has been one of the motivations for prototypes for these designs for new kinds of memory, racetrack memory, where the domain walls separate bits of information and they're manipulated by applying currents. So this is one of the things that's made this a very active area for research. So even in this simplified situation, the LLG equation, Landau, Lifshitz, Gilbert, can't be solved exactly, well, except there's some few known solutions. If you do numerics, then you see a range of different behaviors depending on the strength of the applied field. So here we have, let's say, a low applied field, this H1. And what's shown here are contour plots of polar angle representation of magnetization. So the top plot is theta, that's the angle of M with respect to the axis of the wire, the one axis, and then phi is the azimuthal angle. And position is along the bottom, time along the side, so a horizontal slice is a time slice. And what we see is the domain wall moving at constant velocity, and the attitude of the domain wall indicated by the color, the value of phi, or this color, is staying fixed. If the field is increased, then the motion is no longer uniform. It's superimposed on this motion, uniform motion of the domain wall are these oscillations, and the variation in color in the phi plot says that phi is also changing in time, and so the domain wall is actually processing about the wire as well. And if the field is increased in strength, then these oscillations become more rapid, and we notice that, maybe at first surprisingly, that as the field increases, the velocity of the domain wall actually, or the mean velocity actually decreases. And if you look at how velocity varies with applied field, this is what you see, that there's this regime where velocity increases with applied field roughly linearly, parameters, and then at some cutoff, which can be calculated, there's a change, there's a bifurcation, and then you see these oscillating solutions, and the mean velocity decreases rapidly with applied field. So we'd like to describe this behavior in a simple way, and this is how these collective coordinates are used. So first we want to get a Hamiltonian description. There are different approaches to this, but I'll follow the prescription that I've described already. So first we need the Hamiltonian formulation of the LLG equation. So we'll take as our phase space now magnetization fields on our domain, unit vector fields with square interval gradients and subject to some boundary conditions. For the symplectic form of the space, it's obtained as follows. So symplectic form is some antisymmetric bilinear form on tangent vectors in the phase space. So delta U and delta V represent displacements to two nearby magnetization profiles to M, and the symplectic form evaluated on them is obtained as follows. So at each point X I have the magnetization M of X, and I have these two displacements, delta U and delta V, perpendicular to it. And the area of the parallelogram that they span is integrated over the domain, and that's the symplectic form. And then this abstract Hamilton's equation is just the LLG equation without dissipation, and then dissipation can be added in as before. So to get a description of domain wall motion, so now our domain is a one-dimensional wire. I take any magnetization satisfying the boundary conditions for the domain wall. That's this M of T at trial profile. It might not be the one that minimizes the energy, the one that I wrote down earlier. And now I'll consider a family obtained from these by translations and rotations about the axis of the wire. Translations parameterized by position S and rotation by angle psi. So now in our infinite dimensional space base space, we've identified this constraint manifold, which is just a cylinder, two-dimensional. And so now we restrict the symplectic form to this cylinder. There's only one non-trivial quantity to 2x2 antisymmetric matrix. There's only one non-zero element, which is evaluated on, say, displacements in the angular and translational directions. It's a simple calculation. It turns out not to depend on the trial wave function. It's always equal to 2. It just comes from the boundary conditions. And then we want to restrict the micromagnetic energy to this family. So that just means evaluating the energy for these rotated and translated solutions. And the constraint dynamics we get from this the constraint Hamiltonian dynamics is of this form, and then we add in damping. I'll say what these functions are in a minute, but so here's when we add in damping, we get this system for the angle psi in position S, and there appear these F and G's, which are derivatives of the restricted Hamiltonian with respect to S and psi. This F is a constant. This J might be some current that's coupled to the domain law. And this G is a function of psi only, so there's translational invariance. There might not be rotational invariance because there can be transverse fields or anisotropy, which breaks the rotational invariance. Okay, so it's a simple system to solve, and in fact, the translational dynamics S is slaved to the orientational dynamics psi. So this psi dot is just first order scalar ODE, and so it's easy to understand the dynamics. It's determined by the number of zeros of this function of psi. If there are zeros, and the zeros will typically come in pairs, then psi dot will approach one of the stable zeros, and therefore S dot, so psi dot will go to 0, and then S dot will go to some constant, and this corresponds to these uniformly translating domain walls. If there are no zeros, so some parameters change, like the applied fields, zeros annihilate in pairs. If there are no zeros, then this G is just a periodic function. Psi dot is no longer 0, it will be oscillatory, and then S dot will be oscillatory plus translation, and we see these wavy solutions emerging. And quantitatively, if you take this trial profile to be the optimal profile, then this fits well with what you see from numerical solutions of the LLG equation. That is, these collective coordinate equations fit really well with numerical simulations. So we'd like to justify this now, at least at the level of formal asymptotics, and then we can go further and obtain rigorous results. That's more work. This will just be formal asymptotics. So we need a small parameter, and we'll say that the applied field along the wire is small, first of all. And that means the dynamics will be slow, so this tau is a slow time when it changes by, when the actual time changes by order 1, slow time changes by order epsilon. And they're different than asymptotic regimes one can consider, but we'll take the other parameters, for what I'm about to say, to be small as well. The transverse anisotropy and the transverse components of the magnetic field and the current will also take to be small. Everything is small, and now we expand the magnetization profile in this formal way, and then evaluate order by order. And lowest order, we just get the static equation that m naught is an eigenfunction of this Schrödinger operator, and the solution is just this optimal profile up to, but it's not unique because this is invariant under translations and rotations. And since we're just at lowest order, in principle, these translations and rotations can depend on time, the slow time, tau, and so that's what's indicated here. And now we go to the next order, and now we get an equation for this first correction, which is that this operator script L is related to the Schrödinger operator L I wrote down before. Applied to M1 should be something coming from the right-hand side, the 0th order terms, which can be expressed explicitly in terms of the parameters and then the derivatives of the position and orientation with respect to slow time. In order for this equation to be have a solution, there's a solvability condition, that is that the right-hand side should be orthogonal to the kernel of this operator. And the kernel, it's not hard to see, is spanned by translations and rotations. And so the solvability conditions give you equations for psi dot and s dot, given here. And they're exactly the same as the ones that we got previously from this restrictive variation principle. So it's more effort to obtain them this way, but they coincide. And so now at least we understand why in these settings the collective coordinate approximation should work well. It's much easier to apply, but you can't really establish its efficacy analytically on its own. It's uncontrolled approximation. The next example I want to talk about is one where actually it appears there isn't a collective coordinate representation. It will also describe domain wall motion, but in a different regime where, let's say, the ansatz that we made just gives completely the wrong result. So identified in passing this bifurcation where the domain wall motion has increased the field along the wire. There's a change from this traveling wave solution with increasing velocity to the onset of precession and retrograde motion, and that occurs at this Walker field, which is this critical field given here. So below this critical field you get traveling waves, above it you get oscillating solutions. And here are the two different behaviors. Now, there's a second critical field, which is easier to identify. This is just the field at which one of the static uniform domains becomes unstable. So if the applied field is less than this anisotropy along the wire produces an effective magnetic field also along the wire. And if the applied field is, and the direction of this anisotropy field depends on the direction of magnetization. So if the domain is pointing to the right, so is this anisotropy-induced field. If it's pointing to the left, then likewise. Anyway, so if you have a domain wall, then in an applied field, in one case the applied field is aligned with the domain, in the other case it's against it. And when using these parameters, when the applied field is less than the anisotropy, then the misaligned or anti-aligned domain is stable. But if it becomes big enough, it overcomes the anisotropy, and then there's only one stable domain pointing along the field, and the other one is unstable. And in this regime, then, on the applied field, you see a new solution emerging, say, from numerics. So here, this is again a space-time plot, counterplot of the polar angle theta, angle of m with respect to the axis of the wire. So initially, it's put in this the domain wall. The initial condition is taken to be this optimal profile, and initially it moves with rather slow velocity. And then there's a transient period, and then there emerges a different traveling wave, which is moving much faster, and it's much wider. And here are time slices of both the theta profile in blue and the phi profile in red. So you can see that phi is, this is no longer, the profile is no longer lying in a plane. Magnetization is winding around the axis of the wire as it goes from one orientation to another. So these solutions do have a characteristic velocity and precession frequency, and the profile appears to be rigid. They're non-planar, as I mentioned, and magnetization doesn't remain in a plane. And the width turns out to scale roughly in this way. In particular, it's proportional to 1 over this damping parameter alpha, which I should have identified explicitly previously. All right, this is the damping coefficient in front of the damping term, and it's typically quite small. So this with other things being controlled is larger than the main one we saw previously. And then you see these oscillations about the equilibrium direction in the tails, which look like these spin waves, and they can either wind the same way in both tails or in opposite directions. That's indicated here. Here they're winding in the same ways, but a different, spin waves have the same, let's say, wave number in same chirality, both tails with different wave numbers, or they can have opposite chirality, wind in opposite directions. And the frequency for these solutions appears to grow linearly with the applied field, but the velocity grows as the square root of the applied field. So this won't come out of the collective coordinates, at least not the ansatz that we used previously, because, well, we saw what behavior we could get from it, and it's nothing like this. This problem is really similar to kind of a standard class of problems in reaction diffusion equations or population dynamics. These are go by different names, so propagation into an unstable front, or particular example, the Fisher KPP equation. So here's a model example of these problems. So it's a nonlinear diffusion equation given here, where the reaction term R has two equilibria when psi is equal to naught and psi is equal to 1. And we'll take boundary conditions where psi is going from one equilibrium, 0, at minus infinity, to the other, plus infinity. And we look for traveling wave solutions with velocity lambda. And then substituting the traveling wave ansatz into the equation, then you get just an ordinary differential equation. Given here, Q is the name for this field, which you could think of as just a mechanical problem. I mean, treating the derivatives as thinking of the independent variable of this Q as being some fictitious time. There's an equivalent mechanical problem, which is the motion of a particle in a potential, which is U is just R with some damping, and the damping coefficient is the velocity of the traveling wave in the ansatz. And then what you see depends on the stability of these two equilibria. If they're both stable, it corresponds to a mechanical problem where you're going from one hilltop to another, and you're trying to, of different heights, and you're trying to find some damping, which gets you just starting at 1 at t equals minus infinity, getting to the other as t approaches plus infinity, and the solution will only exist for a particular value of the damping. And so there's a unique velocity for a traveling wave solution. The other case is where one of the equilibria is stable, but the other one is unstable, and that corresponds to the mechanical problem going from the hilltop to a well. And, now there's a whole range of values of the damping for which this will be achieved, provided the damping is large enough so you don't overshoot. For any lambda, you'll find a solution of these equations satisfying these conditions, or you'll find a family of traveling waves. But in, let's say, numerical solutions of the PDE, of the reaction diffusion equation, we find, at least for class of initial conditions, a traveling wave emerging with a specific velocity, not a family of velocities. And so you're looking for a selection criteria. Which velocity is selected, is lambda star. And this problem was, I guess, famously studied by KPP, Kolmogorov, Iskanov, and Petrovsky. And the key observation is that if you look at a given value of this profile or wave or psi, then as a function of time, the steepness of the profile at that point can only decrease. And from that, one can show that the traveling wave that's selected for a family of initial conditions which decay towards the equilibrium values sufficiently rapidly, for such a family, so for example, a step profile would be sort of an extreme prototype, then that will evolve into a traveling wave which has a specified velocity, and it's the profile for which, this traveling wave profile for which the equilibrium values are approached most rapidly, or in terms of this mechanical problem where you get to the bottom, let's say, most quickly. And that occurs for critical damping, in this mechanical problem, where the roots of the linearized stability around this stable fixed point become equal. So we see so what we're saying in this regime where we're talking about domain wall motions, where one of the domains unstable, it's similar. And this KPP phenomenon has been studied in domain wall motion in a number of instances by Dupassier and Ben-Gurion, in cases where this transverse anisotropy is very large, in which case the magnetization remains in a plane, and therefore it's described just by a single angle, and the effective equation is reduced to a scalar equation, and then it really does fit into this KPP framework, scalar reaction diffusion equation. For multi-component scalar reaction diffusion equations, it seems the theory is much less developed, and so the results I'll be telling you about, they're not, certainly not rigorous, they're justified a posteriori by agreement with numerics. But just to say, there's another approach, more general but not rigorous, for obtaining selected ray fronts, which is, I think, goes back to Landau really, and described in this review by Sarlus. And the argument goes like this. So here again is the scalar reaction diffusion equation, and there's an unstable equilibrium at naught, and we're looking for traveling wave solutions. So first of all, we'll look at the solution where it takes values near this stable equilibrium, and so then we'll linearize around that value and get linearized equation, which linearized equation, of course, can be solved explicitly by Fourier transform, and there appears this the frequency of the fundamental solutions depends on the wave number by this dispersion relation. So we want to look at the solution in a frame that's moving with velocity v. So we shift to a moving frame. C is the offset, the velocity of the frame, and also this will be a complex scalar reaction diffusion equation. We'll rotate as well. It's an angular frequency omega. So in the rotating and moving frame, the linearized solution to the linearized equation is given by this expression here. And we're interested in how the solution behaves for a long time. And then the integral can be approximated using the method of steepest descent. And we find that the long time behavior is of this form where up to, there's still a position dependent factor which I've left out, but the time dependence is given by the leading order of the dominant term is given by this expression here, where there appears the Legendre transform of this dispersion relation. So now we still don't have a selection criteria. The selection criteria is choose V and omega, so that in this moving frame, this profile appears to be constant. And that's obtained just by setting, well, omega of, for some V should be equal to, this big phi for some V should be equal to omega, and since these are complex quantities, this is two equations which determine both the velocity for the front or the profile as well as a precession frequency. All right, so now back to the problem we were studying for the magnetization profile, which is now free to live on the point in any direction. And to make progress, we'll eliminate this transverse anisotropy. Now the problem has symmetry about the axis of the wire. That simplifies things. So we're looking for solutions, profiles that are translating at some fixed velocity and rotating at some fixed frequency. Substitute this into the LLG equation. Again, we'll get an ordinary differential equation, which we can also interpret as a mechanical problem. And to facilitate that, instead of writing the profile of this traveling wave m star as a function of c, I'm going to give it a new name, call it r, because I want to think of r as a position on the sphere, and it's a function of some fictitious time. And this is the equivalent mechanical problem. It's a spherical pendulum problem, where the pendulum is subject to a number of forces. First, conservative forces. There's, coming from terms in the energy, there's gravitational force, there's also a harmonic force in the z direction. There's also a Lorentz force here, which is effectively produced by a radial, constant radial magnetic field. So it's as if there's a magnetic monopole at the middle of the sphere producing a magnetic field, and this pendulum is charged, so it's feeling the Lorentz force. Then there are two non-Hamiltonian terms. There's a dissipative term, and there's also a torque, non-conservative torque, and finally there's the force of constraint. The boundary conditions are looking for solutions that start with the pendulum pointing up, one domain orientation, and ending up down. And do we find solutions that satisfy those boundary conditions? It depends on the parameters. So for this v, that's the velocity of the traveling wave, but it appears as a parameter of this pendulum equation. If it's not large enough, if the damping isn't large enough, then you don't get such a solution. You just the solution will approach a limit cycle. But for larger values of this parameter, you do find such a solution. Turns out for every choice of v and omega, there is, up to rotation, a unique solution. So we get a family of traveling waves parameterized by their velocities in omega, and we want to determine which one is selected, which one do we see when starting from in numerical simulations of the LG equation. Okay, and this is just showing that depending on the parameters, they can either wind the same way that the two poles are in opposite ways. So by analogy, we can apply either the KPP selection criteria or do the analysis of this linearized analysis. And they both give the same answer. They give these explicit formulas for velocity and frequency as functions of the applied field H1 and the parameters in the problem, including this damping parameter. And they appear to be, I mean, they agree with simulations, and that's what these pictures show. So this is the domain wall velocity and angular velocity, that's angular velocity as a function of the damping parameter for fixed applied field, and then this is a function of applied field for fixed values of the parameter and other characteristics of the profile. Structural characteristics are also described in this way. Now, an important difference between this case I considered at the beginning, small applied fields, is that the initial problem was domain wall between two stable domains. Now we have a domain wall between one stable domain and an unstable domain. And there will always be thermal excitations present, and the unstable domain will eventually will switch to the stable domain even if there were no applied field. And we can estimate how far the domain wall will move before it's overcome by thermal instabilities. And maybe I won't go through this, but it's a simple calculation to estimate the magnitude of deviations away from the equilibrium configuration due to thermal excitations, and we also know the rate at which excitations will grow under the linearized dynamics, and can determine how far the domain wall will travel in the time that these initially very small fluctuations will grow to appreciable size. And for some reasonable choice of parameters, you find that it can travel a significant distance of the field-free domain wall width of the exchange length. So it's about on the order of several hundred exchange lengths. This solution will persist at ordinary temperatures. Okay, so that's what I wanted to tell you. So there are a number of questions that are nice to answer. I mean, this is not several points where this is not rigorous. First of all, just the analysis of the ODE is already some challenge to prove the existence of these heteroclinic orbits in this pendulum problem. But then there's the PDE problem of showing that the solution, the velocity and frequency that we identified really are attractors for a certain class of initial conditions. And as I say, that just the theory for vector-valued reaction diffusion equations, even in one space plus time dimension, is much more complicated. In this case, it can be simplified because really, while m is vector-valued because it's unit length. It lives on the sphere, so it can be thought of as a complex scalar. But still, it's still not straightforward. And it's interesting to examine the transition as h is increased from the solutions in the two parts of the talk. And there may be intermediate regimes where the observed solution is neither one nor the other, but a different kind. This phenomenon is known in this theory of unstable wavefront propagation. There's a different regime of solutions which I haven't described. It may be possible to see this solution, this behavior in very thin nanowires under strong applied fields that make the applied field large enough to overcome one of the domains. Instead of just seeing some incoherent switching, we would actually see this coherent domain wall moving for some substantial distance. And it'd be nice to look for analogs in higher dimensional systems, two-dimensional configurations under strong applied fields where one of the domains becomes unstable. So thanks very much.
Thank you. Questions? Comments?
Just a curiosity, what type of field in real units are you? What type of field strength do you have in mind in real units?
Yes, it's on the order of, and I have to remember, sorry, but it's on the order of 10 to the 3, 10 to the 4 Tesla, I think.
10 to the 4 Tesla?
Oh.
All right, so then I'm sorry, I'm just caught out. And at some point we computed it, and it's sort of at the upper end of what we've seen in experimental papers, or maybe a bit beyond by a factor of 1.5 for the materials that we were considering. No, 1.5, a factor of 1.5 larger than the largest field we saw.
Probably Tesla. 1.5 Tesla.
It's about
That's already.
So,
Yeah.
I think typically they look at 0.1 Tesla or something.
okay.
Oh,
Okay.
So
1000 Gauss.
Other questions? Sorry, there at the very end, you were talking about thermal instability. What was that really referring to? Because was there a temperature there?
only at the end was there a temperature.
Okay.
But the idea is that you have this domain wall of the wire, and you apply a very strong magnetic field so that this domain has become unstable.
Mm.
So now let's take into account temperature effects that these magnetization in this unstable tail is going to be fluctuating due to thermal excitations.
Mm.
And so it's not perfectly aligned with the wire. It's got some random fluctuations, and these will, because of the strong applied field in the other direction, these will grow.
Mm. It's unstable.
Yeah. If these weren't present, I mean, you still have some, I mean, at any point along the wire in the unstable domain, it's still not exactly aligned along. I mean, the magnetization isn't strictly in the along the wire. It's got some transverse component, but that component does grow exponentially. But that exponential growth is what makes the domain wall move. It's the small view of the Rose solution to the full equation. The exponential growth of the individual magnetization is, due to the large, just this domain wall moving.
So if I understand correctly, if you just look at the Ginzburg, the LLG equation, these traveling waves will not be stable in general if you perturb a bit, say, data, initial data?
The solutions I'm talking about here, no, they will be stable to perturbations, or at least we expect, and this is what we see in numerics, they are stable to perturbations in the initial data.
But you really need convergence of the tails.
Yeah, so
Really well prepared, I would say.
Yeah.
Inside you can do something, but convergence exponential with some specific rate.
Yeah.
So they are supposed to be stable.
Well,
Because of this.
So if the perturbations are localized, then
Yeah.
they're stable. But even for initial data that's not close, but that satisfies these asymptotic conditions, the approach to equilibrium is sufficiently rapid, then at least in the scalar case, it will show that the solution will approach this particular time wave solution.
When you're doing numerics, yes, the thermal instability is in some sense can be modeled.
Yes, it's a numerical
And
round.
I don't remember when we see breakdown.
We didn't see it. Maybe, I mean, when we made this damping parameter very large, increase the damping parameter, that increases the instability rate. Then I think then you can get to the point where you magnify the numerical errors enough so that you start, you don't have to wait too long to see that everything breaks up.
Okay, thanks. Any other questions? Comments? Okay, so let's think